So in the last class we have discussed about the designing of staircase. So now we will see the shear bond as well as development length. Okay. Bending is usually accompanied by bending shear, and shear stress thus produced is accompanied by diagonal tension and compression. So what are those? Here you can see a diagonal crack has been formed. So the large value of diagonal tension can be produced, cracking and even failure of the concrete members. Okay, and as the concrete cannot withstand against the tensile stresses move, so if shear stress is large, vertical stirrups or bent up bars should be provided to withstand the tensile stresses. Okay, and beam should be also checked for safety against shear failure. That I will come later on, that how to check against the shear as well as how to make the designing considering the shear. So let's start. So there are some modes of cracking you can see for RCC long span as well as the short span beams. In RCC beams subjected to relatively high flexural stress and low shear stress, the maximum principal tensile stresses in the outer fiber at the peak moment locations. Okay, so here the flexural stress is high, the low shear stress and the maximum principal stress in the outer fiber. But in case of short span beam, generally they are subjected to high shear stress due to heavy concentrated loads and relatively low flexural stress. It is likely that maximum principal tensile stresses are located at the neutral axis at inclination of 45 degree to the longitudinal axis of the beam. The resulting cracks, which generally occurs near the support as shear force is maximum here, as termed as the diagonal tension cracks or web shear cracks, that I have shown you in the figure. Okay, so here the depth is high for the thin waves, high shear stresses and low flexural stresses, and the maximum principal stresses is in the neutral axis that I have told earlier. So the nominal shear stress. Now there are two cases are there. First one is members with uniform depth. So suppose we have a beam like this, and if the depth is constant, that means the depth over here and the depth at each portion, if it is same, so then we will consider this particular formula, that is tau v equals to vu by bd. Okay, so here it is also written that the nominal shear stress in beam of uniform depth, okay, shall be obtained by the following equation. Now tau v is the nominal shear stress as per clause number 40.1 IS 456/2000. Now here it is already written that the nominal shear stress in beams of uniform depth shall be obtained by the following equation. So tau v is the nominal shear stress, vu is the shear force due to design loads, b is the breadth of the member, and d is the effective depth. Okay, so in this way we can determine the value of the nominal shear stress. So whether the shear reinforcement is needed or not, for that reason we need to determine the value of the tau v. Okay, now the nominal shear stress, but here the members with the varying depth. So if the beam is having a varying depth on several places, then we will consider this particular equation, which is given in clause number 40.1.1 in IS 456/2000. Okay, so here it is said that in the case of beams having a varying depth, the equation shall be modified as this one, where tau v you already know, that is the nominal shear stress, and vu, that is same. Now there is a another term, that is tan of beta. What is beta? It is actually the angle between the top and the bottom edge of the beam. Okay, so if we have the variable depth, then we will have this particular angle beta, and then we just need to put the value beta over here and we will get the value of tau v. Now there is case that whether we need to take the value positive or negative. Look, in this paragraph, if you can see, the negative sign in the formula applies when the bending moment is increases. That means when the mu value, that means the moment, if it is increases, then we will consider the negative sign, and vice versa for another case, like if the moment value is decreases, then we will need to put the positive sign. Okay, so in this way we can determine the value of the tau v, that means the nominal shear stress for the varying depth. So for design shear stress, okay, so for design shear stress we need to see the table 19 which is given at IS 456 2000. Okay, so with respect to the value of PT, this is the PT value, right? AS by BD into 100 percentage of steel. Now with respect to the value of PT, and we also know the grade of concrete, like by considering which grade of concrete we are designing that particular thing. So we need to consider that particular grade. Suppose I am considering M20. Suppose I am considering M20 and my percentage of steel is 0.50. So my what will be the value of the design shear strength of the concrete, that is the tau c, that is 0.48. Okay, so in the previously I have shown you how to determine the tau v, and for both cases, that means for uniform section as well as the varying section, and now we got the value of tau c also, right? Now let's go to the next step. Look, this is another thing. We can get the maximum shear stress value, that means the tau c max. This maximum value we can get from table 20. Okay, and the unit is Newton per millimeter square, that means megapascal, from IS 456 2000. Now here with respect to the grade of concrete, the tau c value is given. Look, previously we considered M20 na, and previously we get the value of tau c, that is 0.48, and here the maximum value is given 2.8. so this is the maximum value of tau c which is given at table 20 IS 456 2000. So this is for determination of the maximum shear stress. We need all these three values, that means tau v, tau c as well as the tau c max. Okay, now let's go to the next step. Now minimum shear reinforcement. Now the condition is this: why we need to provide the minimum shear reinforcement, that means in which case we will provide this minimum shear reinforcement. Look here, as per clause number 40.3 IS 456 2000, as per clause number 40.3, the minimum shear reinforcement should be when the tau v is less than tau c. That means in previously we got the value of tau v, right, and we also know the value of tau c from the table 19. Look here, this is table 19. So we just need to check that whether this condition is satisfied or not. That means when the tau v is less than tau c. So tau v is less than tau c. In such cases we need to provide the minimum shear reinforcement. Okay, and this minimum shear reinforcement, what will be the value of this minimum shear reinforcement? That will be according with the 26.5.1.6. so look here, I have already given the 26.5.1.6 clause over here. So as per this clause, here it is written that the minimum shear reinforcement in the form of the stirrup shall be provided in such that ASV by B into SV greater than equals to 0.4 by 0.87 into Fy. Okay, where ASV is the total cross sectional area of stirrup legs effective in shear. Now if I am providing two leg stirrup, suppose two leg stirrup and diameter is 8.5, so what will be the value of ASV? ASV equals to 2 into pi by 4 into 8 square. Okay, now Fy value you already know, this is the characteristic strength of the stirrup reinforcement in Newton per millimeter square. Okay, now here it is which shall not be taken greater than 415 Newton per millimeter square. Okay, so this is very much important. Now SV, this is actually the spacing of the stirrup. Okay, now B is nothing but the breadth of the beam, or you can say the breadth of the web of flanged beam. Okay, now so that means we have checked one condition, that means when the tau v is less than tau c, then we need to provide this much amount of shear reinforcement. Okay, now to the next step. Now look, previously what we have seen, that if tau v is less than tau c, right, that means previously we have seen tau v is less than tau c, then actually the shear reinforcement is not necessary, but yeah, we need to provide the minimum shear reinforcement. But in this case, look here, design as per clause number 40.4, this is also from IS 454, one second, as per IS 456 2000. Okay, now when the tau v exceeds tau c, that means when the value of tau v greater than tau c, and the tau c value is given in table number 19. Okay, so if in these such conditions, that means tau v is greater than tau c, then shear reinforcement shall be provided in any of the following forms. So if this condition occurs, that means tau v is greater than tau c, then we need to provide the shear reinforcement in any of these three forms. So first one is the vertical stirrups, second one is the bent up bars along with stirrups, and third one is the inclined stirrups. So by any of these three forms we need to provide the shear reinforcement. So let's see. Look, shear reinforcement shall be provided to carry a shear equal to Vu minus tau c into Bd. Okay, so each term you already know. Tau c is the design shear stress, B is the breadth, D is the effective depth, and Vu is the shear stress, right? So for first case, that means previously I have told now, for vertical stirrup, second one is the bent up bars, and third one is the inclined stirrup. So look, there are three formulas are given by which you can provide the shear reinforcement. Look here, for vertical stirrups we need to use this particular equation, for inclined stirrup we need to use this particular equation. Definitely if there is an inclination, so there is an angle, right? So here you can see alpha is given, that means it is actually the angle. Look here, alpha, it is the angle between the inclined stirrup or the bent up bars and the axis of the member, not less than 45 degree. Definitely it will be greater than or equals to 45 degree. Okay, now this is the last case for the inclined stirrup. Okay, for the single bar or single group of parallel bars, all bent up bars in the same cross section. So this is the equation for that. Now here you can see ASB, SB, tau v, tau c, all of the terms you already familiar with. So you just need to put the values over here and you will get the value of the shear reinforcement. Definitely we will solve some problems to make it more clear. So very important thing, the development length. So previously in the last semester you have the class of estimation and costing, right? So there I have told you the concept of the development length, and which is denoted by the LD. At the time of bar bending schedule of two-way slab, I have told this particular thing, but how the value of this LD came, now I will show you over here. Okay, this is actually as per clause number 26.2.1 and IS 456 2000. Here the development length LD is given, the formula is phi into sigma s by 4 into tau bd. Okay, so what is the each terms, let's see. Look, phi is the nominal diameter of the bar, and sigma s, it is the stress in bar at the section considered at design load, and tau bd, it is given in the, it is actually the bond stress which is given in 26.2.1.1. so which I have pasted here. Look here, So as per 26.2.1.1, the design bond stress in limit state method for the plain bars in tension shall be given as below. So here you can see the grade of concrete is the design bond stress, that means tau BD in Newton per millimeter square is given with respect to the grade of concrete. So for M20 the tau BD value is 1.2. So similarly for other grade of concrete you can see the value of the bond stress is given, okay, design bond stress. So we just need to select the value of tau BD with respect to the grade of concrete. Suppose I am considering M25, so we need to put the value 1.4, and yeah, phi is the nominal diameter of the bar and sigma s, that is the stress in the bar at the section considered as design load. Okay, so similarly I can get the value of development length, that is LD. Now in this picture you can see actually the same bar bending schedule I have shown in the last semester. So here you can see up to from this particular, one second, I am changing the color. So look here, from this point, this particular length up to this, okay, which goes inside the column. So this particular length is termed as the LD value. Okay, this is actually the LD, that means the development length. And at the time of bar bending schedule we have considered that it is given, and it is 50D that we have considered previously, right? So now you understand that how that value came. So in this way that particular value came. Now there are some special note is there for deformed bars conforming to IS 1786. These values shall be increased by 60%. Okay, so that means the value which is given over here, that means the value of this tau BD is increased by 60% for the deformed bars. Okay, and for bars in compression the values of bond stress for bars in tension shall be increased by 25%, and the value of bond stress in working stress design that are given in B 2.1. So if you want to design that in a working stress method, so that particular values are given in B 2.1 in IS 456 2000. Okay, so very simple one. Now the bend and hooks. Okay, so in case of stirrup reinforcement, the clause number 26.2.2.4 IS 456 2000, okay, and under 26.2.24 and point number B, so what it tells that it specifies that complete anchorage shall be deemed to have been provided if any of the following specification is satisfied. So what are those specifications? Look here, 90 degree, 135 degree and 180 degree, these three value is given. So considering these three values, I have shown you these three figures. So here you can see this is for the 90 degree bend, this is for 135 degree and this is for 180 degree. So the first point, that means for 90 degree, what it says that the first specification that needs to be satisfied, 90 degree bend around a bar or diameter not less than stirrup diameter, here it is D, small d, with extension of at least 8D. So here you can see this is the extension of at least 8D. Okay, similarly for 135 degree, here the extension value is 6D, that means 6 into the diameter of the bar. Okay, and for 180 degree the bend with extension of at least 4D. So here it is 4D. So the anchoring shear reinforcement shall be deemed to have been provided if any of the following specification is satisfied. Okay, so this is the last part of this particular chapter. So now we will solve some problems related to this. Okay, thank you.